In mathematics, given a group G under a binary operation, a subset H of G is called a subgroup of G if H also forms a group under the operation. More precisely, H is a subgroup of G if the restriction of 2H times H is a group operation on H. This is usually denoted Hg. Readers, H is a subgroup of G. The trivial subgroup of any group is the subgroup E, consisting of just the identity element. A proper subgroup of a group G is a subgroup H which is a proper subset of G. This is usually represented notationally by H less than G. Readers, H is a proper subgroup of G. Some authors also exclude the trivial group from being proper. If H is a subgroup of G, then G is sometimes called an overgroup of H. The same definitions apply more generally when G is an arbitrary semigroup, but this article will only deal with subgroups of groups. The group G is sometimes denoted by the ordered pair, usually to emphasize the operation when G carries multiple algebraic or other structures. This article will write AB for a B, as is usual. Basic properties of subgroups. A subset H of the group G is a subgroup of G if and only if it is non-empty and closed under products and inverses. In the case that H is finite, then H is a subgroup if and only if H is closed under products. The above condition can be stated in terms of a homomorphism, that is, H is a subgroup of a group G if and only if H is a subset of G and there is an inclusion homomorphism equals A for every A from H to G. The identity of a subgroup is the identity of the group. If G is a group with identity EG, and H is a subgroup of G with identity A, then A equals EG. The inverse of an element in a subgroup is the inverse of the element in the group. If H is a subgroup of a group G, and A and B are elements of H such that AB equals bar equals A, then AB equals bar equals EG. The intersection of subgroups A and B is again a subgroup. The union of subgroups A and B is a subgroup if and only if either A or B contains the other. Since, for example, 2 and 3 are in the union of 2Z and 3Z, but their sum 5 is not. Another example is the union of the x-axis and the y-axis in the plane. Each of these objects is a subgroup but their union is not. This also serves as an example of two subgroups, whose intersection is precisely the identity. If S is a subset of G, then there exists a minimum subgroup containing S, which can be found by taking the intersection of all of subgroups containing S. It is denoted by less than S greater than and is said to be the subgroup generated by S. An element of G is in less than S greater than if and only if it is a finite product of elements of S and their inverses. Every elementer of a group G generates the cyclic subgroup less than or greater than. If less than or greater than is isomorphic to Z, nZ for some positive integer n, then n is the smallest positive integer for which n equals E, and n is called the order of A. If less than or greater than is isomorphic to Z, then A is said to have infinite order. The subgroups of any given group form a complete lattice under inclusion, called the lattice of subgroups. If E is the identity of G, then the trivial group E is the minimum subgroup of G, while the maximum subgroup is the group G itself. Cosets and Lagrange's theorem. Given a subgroup H and some are in G, we define the left coset R equals R, H in H. Because A is invertible, the map phi HR given by phi equals R is a bijection. Furthermore, every element of G is contained in precisely one left coset of H. The left cosets are the equivalence classes corresponding to the equivalence relation A1 tilde A2 if and only if A1 minus 1 A2 is in H. The number of left cosets of H is called the index of H in G and is denoted by G. H. Lagrange's theorem states that for a finite group G and a subgroup H where G and H denote the orders of G and H, respectively. In particular, the order of every subgroup of G must be a divisor of G. Right cosets are defined analogously. H equals H, H in H. They are also the equivalence classes for a suitable equivalence relation, and the number is equal to G, H. If R equals half A every A in G, then H is said to be a normal subgroup. Every subgroup of index 2 is normal. The left cosets, and also the right cosets, are simply the subgroup and its complement. More generally, if P is the lowest prime dividing the order of a finite group G, then any subgroup of index P is normal. Example: subgroups of Z8. Let G be the cyclic group Z8 whose elements are and whose group operation is addition modulo 8. Its Cayley table is this group has two non-trivial subgroups, J equals 0, 4, and H equals 0, 2, 4, 6, where J is also a subgroup of H. The Cayley table for H is the top left quadrant of the Cayley table for G. The group G is cyclic, and so are its subgroups. In general, subgroups of cyclic groups are also cyclic. Example: subgroups of S4. Every group has as many small subgroups as neutral elements on the main diagonal. The trivial group and two-element groups Z2. These small subgroups are not counted in the following list: 12 elements, 8 elements, 6 elements, 4 elements, 3 elements. Other examples: an ideal in a ring is a subgroup of the additive group of. Let be an abelian group. The elements of that have finite period form a subgroup of called the torsion subgroup of.